Ever wondered about the magic that happens behind the scenes to ensure a consistent voltage supply in your home or office? Today we're going to unfold the mystery behind the principle of voltage control in a distribution network. Voltage control, in its essence, is all about maintaining a balance. Picture a high voltage to medium voltage transformer, for example 70 to 20 kilovolts. The voltage on the secondary side is kept within a certain deadband by means of the automatic tap changer of the transformer. As power consumption increases or decreases, the voltage along the medium voltage feeder varies. It drops when consumption is high and rises when consumption is low. Now imagine a long feeder stretching away from the main substation. The further away you go, the lower the voltage on the medium voltage feeder becomes. To counteract this, different turns ratios are used in medium voltage to low voltage transformers, sometimes referred to as offload tap changers. The turns ratio is smaller at the end of the feeder, which boosts the voltage on the secondary side. This technique can boost the voltage in the distribution network by up to 5%. But voltage control isn't a free-for-all. It must be carefully managed to stay within an undervoltage limit and an overvoltage limit. These limits are the subject of ongoing discussions, but regardless of the specific numbers, the basic coordination principles remain the same. The deadband is typically set slightly above the nominal voltage to accommodate for voltage drop along the feeders. The voltage for the most remote customer during maximum load should still be above the undervoltage limit. However, during low load, the voltage should not exceed the overvoltage limit for any of the customers. The critical case for overvoltages is not the most remote customer, but the one nearest to the main substation with voltage boosting. The difference between the highest voltage magnitude for a given customer and the overvoltage limit is referred to as the overvoltage margin. The introduction of distributed generation results in less voltage drop when the generator is producing active power. This leads to a smaller overvoltage margin, and the maximum voltage may even exceed the overvoltage limit. When this happens, the power system no longer fulfills its primary aim to maintain the voltage magnitude within limits, and the hosting capacity is exceeded. To summarize, voltage control in a distribution network is a finely tuned balance. It involves the use of automatic tap changers and different turns ratios in transformers to keep voltage within a set deadband. It's a system that ensures the voltage supplied to both near and far customers remains within acceptable limits, regardless of load. However, the introduction of distributed generation is adding a new layer of complexity to this balance, potentially impacting the overvoltage margin and pushing the network beyond its hosting capacity. So, the next time you switch on a light or power up your computer, spare a thought for the intricate dance of voltage control that's happening behind the scenes to keep your electricity supply stable.